Welcome back. This is Fundamentals of Micro and Nano Fabrication. I am Sushobhan Awasthi and this lecture is on ion implantation. This is the second half of the lecture on ion implantation. In the previous lecture, we had looked at what is ion implantation, what parameters do we control, specifically dosage and energy, how do things change with the size of the weight of the ion, the energy of the ion and the dosage of the ion. And we had briefly discussed some non-idealities that occur, for example, channeling and backscattering. In this lecture, we will delve into a little more detail and look at some of the more advanced aspects such as arbitrary profiles, repair, rapid thermal annealing, and yeah, let's get started. Channeling is not the only thing that leads to asymmetry. Another one is backscattering. So, what is backscattering? Backscattering is that supposing the ion that is coming in has a much lower mass than the silicon atom. So, imagine billiard ball. So, what you are trying to do is you are taking a say a ping pong ball and hitting a billiard ball with it. So, billiard ball is silicon, the ping pong ball is say boron. So, lighter and smaller. If you do a mental experiment, you can easily see that if you hit the ping pong ball onto the billiard ball, the ping pong ball will come back and the billiard ball may not move much. So, if you do the implantation and you look at this figure, depending upon at what speed do you push the boron in, if you try to push the boron at very high speed, the boron will just backscatter. It will just hit silicon and come back. And in the profile, the implanted profile, you will actually see that compared to the dotted case, which is ideal simple Gaussian profile, the profile will be a little higher at the front edge and a little lower at the back edge. So, this backscattering phenomena creates these front biased asymmetric profile in boron. The problem is slightly is not slightly, it's actually completely inverted in the case of antimony, where antimony is now the heavier atom. So, now imagine you are shooting billiard balls at a lattice of ping pong balls. Now, the billiard ball is very heavy. So, now it will knock this ping pong ball off its place. And that is what you see in the profile. So, if boron is biased towards the front, the antimony is biased towards the back, and this effect is magnified at higher energies. So, if you are doing dopants at very high energies, say 500 kilo electron volt or 1 million electron volt, then you have to be careful about backscattering. A very nifty use of ion implantation is in creating arbitrary looking profiles. If you remember diffusion, making the diffusion is something between an error function or a Gaussian profile. It is very hard to make it anything else. Supposing you do a diffusion and you make a profile and then you go back and do a second diffusion to try to create a new profile. While you are doing the diffusion of the second process, it will change the profile of ions of dopants that you created in the previous step. So, successive diffusion steps keep changing the previous ones in a manner that is very hard to reliably make a new shape. Implantation does not suffer this problem. Fundamentally, implantation is being done at room temperature. The wafer has not been heated yet, right? So, the dopant ions cannot diffuse much, so they are frozen in time. So, you can create an arbitrary profile by just doing successive implantation. So, if you look at an example on slide 20, supposing you were to first do a dopant ion implantation at say low energy 24 kilo electron volt. So, you will get a shallow green color profile. The next, just after that, without heating the wafer, you now do a second implantation at a slightly higher energy, and then at even higher energy, and then at even higher energy. What you will actually see finally is this red looking curve, which is just a sum of all these individual component implantations. And after this, you do the anneal step to do dopant activation. What you have achieved is a very uniform looking profile at the surface. Now, such uniform profiles are very hard to make through diffusion, but are possible with ion implantation, and that is one of its great advantages. Now, let us talk about implant damage, which, as I hinted before, always happens and is one of the primary reasons why implantation was technically challenging for a long time. So, let us look at this slide, and whatever I am going to say I have said before, but this is just to give you a visual idea of what I am saying. Supposing you take a light ion and it's coming with a certain amount of energy, it will suffer collisions, and with each successive collision it would lose some of its energy and come to a standstill at some point, right. The depth will depend upon what energy it's coming through. But while the ion is doing this solid black line, the silicon atoms themselves are also getting displaced, right. So, these small arrows represents that at each successive collision a silicon atom will get displaced, and whenever a silicon atom gets displaced, it might then do some second order collisions with other silicon atoms, so even more silicon atoms will get replaced. So, overall, once an ion goes through a certain material like silicon, it leaves behind a region of damage. So, it is not just a line of damage, but a region of damage, and that region of damage will scale with how heavy your light ion you are implanting. So, for example, a light ion will go very deep, right, but it will create a slightly narrower looking shape. On the other hand, a heavy ion like antimony or arsenic would not go very deep, right, but still the energy is the same, right. So, the energy needs to be dissipated, so that all that energy that must be dissipated is concentrated over a smaller depth, so must have a larger area. So, that is what is happening here. So, the successive collisions will be the silicon collisions, and the dislocations will be higher in the case of a heavy ion than a lighter ion. So, you end up getting a slightly larger damaged region. So, what does the silicon surface looks like? So, supposing you start with a very nice looking silicon lattice and you shoot with ions at say 100 keV of energy. So, after a certain point when you finish your implantation, you would not have a good looking lattice, you would actually have a very damaged looking lattice where a lot of these silicon atoms have been moved. If you just do some simple math, the displacement energy of moving a silicon atom is around 15 eV, okay. And you are shooting it with ions of energy say of 100 keV. So, now this is 15 eV, this is 100 keV. So, this is around 1000 to 10,000 times different. So, on an average, one implanted atom which is coming from at energy of 100 keV will end up displacing around 1000 to 10,000 silicon atoms, right. So, that is why it has that huge damaged region. Now, what can we do about it? Thankfully, this is an unhappy situation, right. So, this is a damaged silicon lattice, and in this damaged silicon lattice every now and then you have a dopant. Now, neither the silicon nor the dopant are actually in their lowest energy state, they are sort of somewhere in the random. The lattice has been destroyed, so there is no lattice, they are not necessarily in a lattice position, but this is a high energy state. So, if you were to anneal this system, if you were to take the system to a higher energy, then the system would like to reduce its energy. It will have enough diffusivity of atoms to be able to reorganize and find its lowest energy position. And in that lowest energy position is when all these atoms are at the lattice position. So, not only will this anneal away your damage, but it would also allow you to now put these dopant atoms at a substitutional position, and at the substitutional position is when they start giving you electrical doping. This process requires certain temperature, typically around 500 to 1000 degrees C. What type of defects can be fixed like this, what type of defects cannot be fixed like this, all depends upon what type of defect you have formed. Some defects take lower energy, so they can be annealed away at lower temperatures. Some defects require higher energy, so they have to anneal at high temperature. The details really depend upon how much defect you can tolerate. Implantation will always cause some damage. It's very hard in some way, unless there are some very unique cases which I will show later, where all of the damage gets annealed away. Some damage remains, you just have to find the damage that you can tolerate and do annealing appropriately. So, damage is one thing. Let me explicitly talk about dopant activation a little bit. So, supposing you did anneal at say 800 degrees C. So, do an implantation and you do an anneal at 800 degrees C, and that 800 degrees C is enough to fix some amount of damage and get some amount of dopants to the substitutional position, but is not enough to completely put all the dopants into substitutional positions. So, what that can lead to is that even though you have certain dopants or you have a lot of dopants, not all of these dopants are actually electrically active. So, if you were to go and measure electrically acting dopants, then you would get this dotted line. So, these are the free carriers, these are the carriers that are coming from the dopants, and all of this difference between this solid and dotted line are all excess carriers, excess dopants that have not at a substitutional position or are not electrically active. In general, if this is what you see, just by annealing at a higher temperature, you can now move some of these unactivated ion implanted atoms to their correct substitutional position and increase your percentage of activation. In general, around 900,000 degrees C, you start to see almost complete activation. So, your thumb rule, make sure that you anneal your implant at around 900 degrees C or 950 degrees C to get nearly perfect or 100% yield of your dopants. One consequence of having damage being created is that you can actually make your films amorphous. This seems a little weird, but if you think about it, it is not counterintuitive. You are starting with a perfect silicon lattice, you are imparting, you are bombarding it with these heavy ions, and each ion is coming up with so much energy, right? More than 1,000 times the energy it takes to displace one silicon atom. So, each atom is coming and moving around 10 to the power 3 silicon atoms. That's a lot. That's a lot of amplification, right? So, at some point, if there must be some dosage at which you have bombarded so many dopant atoms that all silicon atoms have been displaced from their position. And when all silicon atoms have been moved from their position, what you essentially have is not crystalline silicon, but amorphous silicon. So, that is what I am trying to show visually here, right. So, at lower dosages, you are creating these disordered zones, right, these relatively large disordered zones, and at high enough dosage, these disordered zones will start overlapping to a point where there is a continuous disordered zone, and that continuous disordered zone is essentially amorphous silicon. If you notice the numbers, this number, as you can actually again back calculate, you can do some back of the envelope calculation. So, this is this transition where it becomes completely amorphous is sort of happening around mid 10 to the power 14, right, and this you can sort of see. So, supposing you let's start with this number, right. So, around 1,000 silicon atoms are displaced for every implanted atom. In order to have amorphous silicon, you need around 10 to the power 19 dopants. Why? Because there are 10 to the power 22 silicon atoms per centimeter cube, and if it takes 1,000 of them to be displaced by one atom, then just having 10 to the power 19 dopants per centimeter cube is enough to displace all silicon atoms. And for around 10 to the power 19 dopants, you need 10 to the power 14 dosage at a penetration depth of around 100 nanometers, right. So, penetration depth of 100 nanometer and a dosage of around 10 to the power 14 will give you 10 to the power 19 dopants. So, at around 10 to the power 14 dosage, you do tend to get overlapping, disorder zones and start getting amorphous silicon. You would think this is bad, right, because we started with, while doing crystal growth, we had done so much work to get this perfect silicon lattice, and by just doing ion implantation at high enough dose, we are completely obliterating it and getting amorphous silicon. But trust me, this is useful, and why, we will come to it in a minute. It turns out, however, that this disordered zone does anneal relatively easily, and that is partly because the silicon really likes to grow into a crystal lattice. So, if you were to go and look at what is the activation energy for this process of making amorphous silicon into crystalline silicon, that is only around 2.3 eV. So, at very low temperatures around 550 or 600 C, this amorphous silicon layer gets annealed away, or the damage can be annealed away. It goes through a mechanism that is called solid phase epitaxy. The solid phase epitaxy restores crystallinity. So, you remake your crystalline silicon at very low temperatures, which is good, but also it activates around say 50 to 70% of your dopants, which is a relatively high number. And this rate of SPE is very high, and in fact it is higher for silicon 100 than it is for silicon 111, and that is sort of easy to understand. Even during crystal growth, I had commented upon why certain facets of crystal grow more easily than others. So, this regrowth temperature also follows that trend. And if you do the numbers in order to do around 100 nanometers of solid phase epitaxy, it only takes around 10 minutes at 550 C, which is not a lot. So, at relatively mild conditions, this formation of this amorphous layer can completely be recouped, which is very important, right? Which is very, very important. Now, the existence of solid phase epitaxy leads to a certain non-ideality in how you would think about ion implantation. And what is this non-ideality? I have tried to show in this figure. So, if you look at this slide 27, the simple way of thinking would be that damage is bad. So, it is always better to do an implant at low dose, at low energy, so that you cause small disorder zones that can then be annealed away, and that is true. So, low dose implants will in general lead to better films. Then you would think that as you increase the dopant, then this problem will become more complicated, because there are now more disordered zones, and each disordered zone will anneal slightly differently, and it will take more energy and more temperature to anneal away these defects, which will lead to slightly poorer quality films, and that is true too. So, till now we are okay. Now, you would think that if I now do very high dose, the problem will be even worse, right? But because you are forming this amorphous layer, and that amorphous layer can get annealed at very low temperature, there is this weird case where instead of making the problem worse, you have actually made the problem easier. So, at very, very high dose where you form an amorphous film, the temperature it takes to anneal away the damage actually is lower than what it would have been in the moderate case. And this lower temperature is easier to do than moderate or low dose. So, the high dose implants are actually easier to do annealing off than a moderate dose implant. And that was a counterintuitive example, and it is just one of those lucky things that happened in processing that led to the adoption of implantation. So, it is a happy accident, right. Now, in a lot of ion implantations, the goal is to get to this high dose case. So, you want to get to this high dose case. So, how do you do that? Well, one easy way to do that is always make sure that you do very high dose implants. So, this is what is often called critical dose. For different elements, this critical dose is different. So, for boron, you need to implant more to create damage. For antimony, you need to implant less to create the same amount of damage. This critical dose actually also depends upon substrate temperature. So, this is the substrate temperature not for anneal later, but during the implantation itself. So, if you do the implantation at higher temperature, for example, then some of the damage gets annealed during the implantation itself, and that is bad because that increases the threshold of amorphization. But if you were to do implantations at low temperature, now this self anneal does not happen. So, the dosage of amorphization actually falls. So, if you want to create amorphous films at lower temperature, you just do cryogenic ion implantations, which are a little expensive but possible to do. The second thing that sometimes people do is, if you cannot do high implant, is to do pre-amorphization. And what can you use to do pre-amorphization? Well, you can just do silicon implant. So, you can do a silicon implant in silicon to create damage, and then do an implant after that of whatever atom you want to implant. So, here is an example where silicon damage was done using silicon. So, without silicon pre-damage, you get this sort of profile. And why do you get this profile? Because there are channeling is happening. But if you do the silicon pre-damage, then you have completely destroyed the lattice structure. You now have amorphous silicon on the top, and when you do implantation in the amorphous silicon, there is no channeling. So, you get this sharp Gaussian looking profile that you see on slide 29. So yeah, so that's one way through creating amorphization without high doses. The side effect obviously you see is that there is reduced channeling, there is low temperature anneals. So you don't need to take to high temperature to anneal the damage, and very controlled dopant profile. So this dopant profile looks much closer to a Gaussian than the one that you got before without damage. However, this does increase the cost, so is only done in rare cases. Finally, we have already sort of discussed diffusion. The thing to remember here is that when you are annealing the damage, diffusion will also occur. So during the anneal, expect the ion profile to slightly change. So here is an example. Supposing you did an as implanted profile of arsenic, which is blue, and then you start annealing to activate the dopant and also to remove the damage. During that process, the ions will move. Now, ions cannot be created or destroyed. So from a perspective of diffusion, this is a fixed or a finite dopant diffusion case. So in the finite dopant diffusion case, the dose remains the same, and when the dose remains the same, the peak concentration falls, and the depth of the diffusion increases. So that is what you are seeing in the red and the orange curve. As you anneal more and more, the peak concentration falls and the dopants diffuse in further. Now, this is a challenge. This sort of change in the profile is a challenge in the modern CMOS fabrication, because here we are trying to make very shallow implants. So if you want to retain the shallowness of your implant, then you can't do very long anneals. So what people do is what is called rapid thermal anneal, where the temperatures are still high because you need these to anneal away your defects, but the times are very short. Instead of say 10 minutes, 20 minutes, which are typically in a furnace, you can do things in 60 seconds, 10 seconds, 15 seconds. And if you remember, the depth of a diffusion, right, is under root of dt. By cutting down the time so heavily, you are now reducing the diffusion of the carriers, diffusion of the dopants. So there is just very little time for carriers to diffuse in, for the dopants to diffuse in, so the dopant profile is maintained. And the reason we are able to do this is because the repair process is much faster than the anneal process or the diffusion process. So diffusion takes a little while the repair happens instantly. So this small amount of time is enough for the lattice to repair itself, but not enough for dopants to diffuse. Finally, I would like to discuss the concept of masking. I have already introduced this during diffusion. The basic idea is that you never have blanket dopants. You always need to have a patterned dopant. So one way to make a patterned dopant is to add certain film on top that prevent your dopants from going through. So that is called masking. So during the diffusion process, we discussed how silicon dioxide and silicon nitride are good masking layers. So can we use the same masking layers for implantation too? And the answer is not very effectively. Unlike diffusion, silicon dioxide and nitride are not very good masking layers for implantation. And the reason is that the projected range, which is how deep the implant will penetrate the film, is not very different from silicon and silicon dioxide. So the solid line here is for silicon, the dotted line is for silicon dioxide, and you see for boron the difference is minimal, the phosphorus, the difference is a little bit there, for arsenic it's a little bit there, but it's not significant. In diffusion, the diffusion coefficient of dopants in silicon dioxide was significantly lower, like orders of magnitude lower. But for implantation, the penetration depth does not change much. So in order to, what that means is they're masking, if you are masking with silicon dioxide or silicon nitride, the thickness of those films need to be about as thick as the range, in fact a little bit more, to make sure there are no tails. So that makes it a little harder. Thankfully, there are more effective films that can do masking well. And a good example of that is photoresist. So photoresist is something that we will use during lithography anyways. So you can just look at what is the penetration of the dopant ion in the photoresist. And for various energies, if you look at what is the minimum amount of photoresist required to almost completely stop it, the values are typically around 1 micron. And this 1 micron or 2 micron of photoresist is not thick at all, as we shall see during photolithography. This is very easy to do, this is very easy to deposit. So the easiest thing you can do is just during the lithography process create this patterned photoresist on top, but don't remove that photoresist. Get the ion implantation done and then remove the photoresist. So photoresist is your material of choice for masking when doing ion implantation. Try to avoid silicon dioxide or silicon nitride. If you are going to use silicon oxide or silicon nitride, make sure those films are very thick. Right. So here is the minimum silicon dioxide thickness and here is the minimum photoresist thickness. With that, let me end by comparing these two processes that we have discussed for creating dopants. So on the left is diffusion. We went into a lot of detail, and on the right is implantation, where we have gone into a lot of detail. So what is the net effect? How do we compare these two? Now both of them will create a doped region. However, the masking is a little different. On the left, you typically need a hard mask, something like silicon oxide, silicon nitride, which themselves take some high temperature step to deposit. On the right, the masking can be easily done with just the photoresist. That means the masking step is a low temperature step. The photoresist is often spin coated at room temperature, so it's easier to do, very simple to do. The other difference is in the flow of the dopant. Diffusion does not care about direction. So when you do a diffusion and anneal, the diffusion will go in all different directions. So the dopant profile will be isotropic. So that is what I am trying to show here, where the green portion is smooth, right? Because it diffused in this direction almost as much as it diffused in this direction. So if you now are trying to reduce the size of your device, you are probably reducing the size of this hole, right? You are trying to reduce the size of this dope region. But because dopants always diffuse both down and leftwards and rightwards laterally, it's very hard to actually constrain them in very narrow channels, right? So as you are scaling the device down, diffusion becomes a lot more complicated. Implantation, on the other hand, is very isotropic. There is an ion flux, the ions come from the top, and while there would be some diffusion laterally during the anneal process, the implantation process on its own is completely anisotropic. It has a directionality, the ions all go down. There is no lateral movement. So that is very advantageous as you are trying to scale down the devices and trying to make narrower and narrower doped regions. That's one reason implantation is so popular in modern dopings. Then there are limited amount of dopant profiles possible. You can get something between error function or a Gaussian, but say getting a uniform profile is very hard in diffusion. Because you can create arbitrary profiles by just doing a series of implantation is a little more flexible. Very hard to exactly control the doped profile in diffusion. If you remember, we discussed a two-step process. And the reason we needed a two-step process was it was very hard to exactly control the diffusion profile, get exactly the same peak concentration, get exactly the same depth, all because it's a process that is very hard to exactly control. Ion implantation, on the other hand, is much more accurate. The dosage can be measured with arbitrary precision because it's equivalent to measuring charge or measuring current, and we are very good at that. Then because you are measuring multiple profiles and the simulators have gotten very good at it, we have a very good idea of what the dopant profile would look like after ion implantation. And then we can, because we are doing RTA, the small amount of change that will happen during the anneal process is also small, and all of this is an advantage for ion implantation. Diffusion, however, is a batch process. If you have a furnace, you can just put 25 wafers in, you can put 50 wafers in, you can put 100 wafers in. In modern solar cell production, diffusion is used because you can do it on 400 wafers in one turn. Implantation tends to be a more individual process. You can implant on some number of wafers, and you are limited by just how large you can make your implant. A modern implanter that can do 25 wafers is about as large as a room. So if you now want to do 400 wafers, that machine will be 16 times larger. So those are some of the challenges with implantation. So for small volume production, high quality production, high controlled production, which is modern IC manufacturing, implantation is better. For low cost, cheap, easy, large scale doping, diffusion is better, which is what solar people do. So, with that we come to the end of the lecture, and thank you for joining me.